The illusion of stillness. The night sky presents an illusion of stillness. When you look upward, the patterns of light seem fixed, quiet, and unchanging. Yet, every point of light is undergoing a profound, steady process of change. The stars are not static objects. They are participating in a very long, very slow cycle of formation, existence, and gradual fading. This cycle spans billions of years, a scale of time so vast that a single human lifetime is but a fleeting moment. Tonight, we will trace the factual sequence of a star's life. We will follow the slow gathering of dust, the steady warmth of a star in its prime, and the eventual quiet return of its material to the galaxy. The story begins in the deep, cold spaces between existing star systems. Throughout the galaxy, there are vast, drifting clouds of gas and dust. These regions are known as molecular clouds, or stellar nurseries. These molecular clouds are unimaginably large. They sometimes span hundreds of light years across. They are characterized by extreme cold, with temperatures hovering just above absolute zero. In this profound chill, the particles of gas, mostly hydrogen and a small amount of helium, move very slowly. There is no sound, no sudden movement. There is only the slow drift of atoms in the expansive dark. The patient pull of gravity. For a very long time, these clouds remain in a state of quiet equilibrium. The internal pressure of the cold gas pushes outward. This is perfectly balanced by the faint, persistent pull of the cloud's own gravity pulling inward. However, this balance is sometimes disturbed. A slow-moving density wave passing through the spiral arms of the galaxy can shift the gas. The gentle push of stellar winds from a distant older star can also cause the gas and dust in a particular region to compress slightly. When this happens, the balance shifts. Gravity, the most patient force in the universe, begins to take over. As a pocket of the cloud becomes slightly denser than its surroundings, its gravitational pull naturally increases. This increasing gravity causes more nearby gas to be drawn inward. As the material gathers, it falls toward the center of the newly forming mass. This process is not rapid. It takes hundreds of thousands of years for the gas to slowly accumulate. As the material falls inward, the particles begin to rub against one another. This friction generates a very small amount of heat. Over a vast stretch of time, the center of this collapsing cloud begins to warm. It is now a protostar. At this stage, it does not emit visible light. It is wrapped in a thick, insulating blanket of its own dust. It glows only faintly in infrared wavelengths, hidden from typical view. Deep within the core of the protostar, the temperature continues to rise steadily. Gravity relentlessly packs the hydrogen atoms closer and closer together. The pressure builds, steadily and inevitably. The protostar continues to gather mass from its surrounding envelope, settling into a spherical shape. Eventually, the temperature at the very center of the core reaches approximately 15 million degrees Celsius. At this specific threshold, a fundamental shift occurs. The hydrogen nuclei, which typically repel each other, are moving fast enough and are packed tightly enough that they are forced together. They fuse, creating helium. This process is known as nuclear fusion. When hydrogen fuses into helium, a small amount of mass is converted directly into energy. The long equilibrium. This energy radiates outward from the core. For the first time, the outward pressure generated by the heat of fusion at the inward pull of gravity. The collapse finally stops. The star stabilizes. It has entered the main sequence, which is the longest and most stable period of its entire life. For a star similar in mass to our Sun, this period lasts for about 10 billion years. During this vast stretch of time, the star changes very little. It simply sits in the vacuum of space, steadily converting hydrogen into helium in its core. It radiates light and heat out into the darkness. The star is a perfect sphere of balanced forces. Gravity tries to pull the star inward, while the energy from the core pushes outward. They are matched perfectly. The star hums with a steady, consistent energy. It provides a reliable source of light, a calm anchor for any planets that may have formed in orbit around it. As the billions of years pass, the core of the star slowly accumulates helium. This is the natural byproduct of the fusion process. The hydrogen in the very center eventually begins to run low. Without the steady energy of hydrogen fusion to support it, the core begins to slowly compress under the weight of the star's outer layers. As the core compresses, it heats up even more. This additional heat radiates outward, warming the layers of hydrogen gas that immediately surround the core. This introduces a new phase of fusion within the aging star. The hydrogen in this shell surrounding the core begins to fuse, generating a new source of energy. This new outward pressure is stronger than before. It pushes against the outer layers of the star, causing them to gradually expand. As the star's outer layers stretch further away from the heat of the core, they naturally begin to cool down. The light they emit shifts in frequency. The star changes from a bright yellow or white to a deep, warm red. It has become a red giant. This expansion is a very slow process. If you were observing the star over millions of years, you would simply see it growing steadily larger and redder. It is a quiet swelling in the dark expanse of space. A slow expansion. For a star like the Sun, its outer layers will eventually reach out far enough to envelop its closest planets. The red giant phase is a period of slow, inevitable change as the star adjusts to its shifting internal chemistry. Deep inside the red giant, the core continues to compress. It eventually becomes hot enough to fuse the accumulated helium into carbon and oxygen. This provides a temporary new source of stability, but it does not last nearly as long as the main sequence. Eventually, the helium in the core also exhausted. For an average-sized star, the core will never become hot enough to fuse carbon or oxygen. The end of its active life is slowly approaching. The outward pressure begins to falter. Without the outward pressure of fusion to support them, the very outer layers of the red giant begin to drift away. The gravitational hold of the core on these distant, expanded layers is very weak. Slowly, the star sheds its outer envelope of gas into the surrounding space. This gently expanding shell of gas is called a planetary nebula. It forms a beautiful, faint sphere or ring of illuminated material, slowly drifting outward into the interstellar medium. Left behind in the center of the nebula is the star's exposed core. It is no longer fusing elements. It is entirely composed of densely packed carbon and oxygen. This quiet, glowing remnant is called a white dwarf. A white dwarf is incredibly dense. A teaspoon of its material would weigh tons on Earth, but it is entirely inactive. It is simply a hot, glowing sphere, radiating its remaining thermal energy into the cold vacuum of space. Over billions and billions of years, the white dwarf will slowly cool. Its light will change from white to yellow to a dull red. Eventually, it will fade completely. It will become a black dwarf, a cold, dark sphere drifting silently through the galaxy. The planetary nebula that once surrounded it will have long since dispersed. The gas and dust will mix with the interstellar medium, ready to eventually become part of a new molecular cloud. The path of the massive stars. This gentle fading as the fate of stars with a mass similar to the Sun. However, stars that are much more massive follow a different, though equally natural, path. A massive star progresses through its life stages much more rapidly. Its immense gravity creates extreme pressure and heat in its core. This causes it to burn through its hydrogen fuel very quickly. A massive star might consume its initial fuel in a mere few million years. When the hydrogen is gone, the massive star swells into a red supergiant. Because of its greater mass, its core can achieve the temperatures necessary to fuse heavier and heavier elements. It fuses carbon into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. The production of iron is a definitive turning point. Fusing iron does not release energy, it consumes it. Suddenly, the outward pressure, that has supported the star for its entire life ceases entirely. The core, composed of iron, finds itself bearing the crushing weight of the entire star. The balance of forces is broken. In a fraction of a second, the core collapses in on itself. The outer layers of the star follow, rushing inward at an immense speed. When this infalling material hits the dense, collapsed core, it rebounds. This sends a shockwave outward, expelling the star's outer layers into space. This event is a supernova. A supernova is a profound redistribution of matter. It scatters the heavy elements forged within the star across vast distances. These elements, the carbon, oxygen, iron, and others, will eventually drift and cool. They will mix with clouds of hydrogen to seed the next generation of stars and planets. A return to the dark. What remains after a supernova depends on the original mass of the star. If the core is of a certain mass, the collapse stops when the protons and electrons are crushed together to form neutrons. This creates a neutron star. It is a sphere roughly the size of a city, but containing the mass of a star. It sits quietly in the dark, spinning and slowly cooling. If the original star was even more massive, the collapse cannot be stopped by any physical force. The matter continues to fall inward until it is concentrated into a single point of infinite density. This is a black hole. It is a region of space where gravity is so strong that nothing, not even light, can escape it. A black hole represents a quiet, absolute endpoint. It is an invisible presence settling into the fabric of space. Whether a star fades quietly as a white dwarf or collapses into a black hole, the outcome is a return to stillness. The energy has been spent, the elements have been forged, and the material has been returned to the galaxy. The scattered gas and dust will drift for eons. It will slowly cool in the deep silence of space. Eventually, inevitably, gravity will begin its patient work once again. A new cloud will gather, a new core will warm, and the long, quiet cycle of stellar life will begin anew. The universe continues its slow, steady respiration. Like and subscribe for more incredible facts about our universe. Welcome. The title of this video uses the word horrific to describe the Artemis II mission. While spaceflight involves extreme conditions, there is no need for fear. Tonight, we will look at 10 profound challenges the crew faces. We will explore these facts calmly. The reality of space is not one of horror, but of absolute stillness, careful math, and quiet bravery. Close your eyes, relax your breathing, and let us journey into the deep dark. Our journey begins by understanding the context. Artemis II represents humanity's return to deep space after more than half a century. It is a voyage taking 4 astronauts further than anyone has ever gone. While the mission profile is meticulously planned, the margins for error are incredibly slim. The universe does not accommodate mistakes. We will look closely at these stark realities, framing them not as terrors, but as monumental hurdles overcome by science. Fact 1. The controlled explosion. Fact 1 concerns the sheer violence of the launch. To escape the gravity of our planet, the Space Launch System rocket must generate immense power. The crew sits atop millions of pounds of highly combustible cryogenic propellant. During liftoff, this fuel burns in a controlled manner, creating a thrust equivalent to a small, sustained nuclear event. It is a violent, rattling ascent, but it is precisely calculated to push the heavy Orion capsule into the vacuum of space. Inside the capsule, the astronauts experience crushing physical forces. As the rocket accelerates, the G-forces multiply the weight of their own bodies, pressing them deep into their seats. Breathing becomes a conscious effort, yet the engineers have measured every vibration. The solid rocket boosters burn out and fall away quietly into the ocean. The trembling stops, replaced by the sudden, weightless glide of orbital insertion. The violent beginning ends in utter silence. Fact 2. The void of distance. Fact 2 is the immense, isolating distance from home. The International Space Station sits only a few hundred miles above our heads. The Artemis II crew, however, travels much further. They journey hundreds of thousands of miles into the void, reaching a point roughly 4,600 miles beyond the far side of the Moon. This is further than any human has ever traveled. The scale of this distance is difficult for the human mind to truly grasp. In this deep expanse, the familiar markers of day and night vanish completely. Earth appears only as a small, pale marble suspended in an infinite sea of absolute black. From their vantage point, the entirety of human history, every continent, and every ocean fits behind the space of a single thumbnail. It is a humbling, beautiful sight, but it carries the heavy psychological weight of complete detachment from the world they have always known. Fact 3. The mechanics of no return. Fact 3 is the lack of an immediate rescue option. If an emergency occurs on a low Earth orbit station, astronauts can enter a return vehicle and splash down in a matter of hours. For the Artemis crew, there is no quick return. Once they commit to the translunar injection burn, they are bound to the unyielding mechanics of orbital physics. They cannot simply turn the ship around. They must complete the long loop around the Moon before Earth's gravity brings them back. This reality means they must be entirely self-sufficient. If a critical system fails days into the journey, they cannot wait for a rescue ship. They must rely entirely on their own training, the redundancy of their life support systems, and the steady guidance of mission control transmitted across the void. They are for individuals floating in a fragile metal bubble, reliant on calm, methodical problem solving to survive any anomaly that arises in the dark. Fact 4. Beyond the magnetic shield. Fact 4 involves the invisible danger of deep space radiation. Earth is surrounded by a protective magnetic bubble called the magnetosphere. It shields our planet from the harsh radiation of the Sun and the broader galaxy. Artemis II is the first crewed mission in over 50 years to leave this safe harbor. As they pass beyond the Van Allen belts, the astronauts are exposed to a fundamentally different environment, unprotected by the Earth's natural defenses. The quiet space between worlds is filled with high-energy particles moving invisibly in the dark. These cosmic rays pass seamlessly through the hull of the spacecraft and through the bodies of the crew. Over time, this exposure can damage DNA at a cellular level. The risk is carefully managed with specialized sensors and shielding, but it is a silent, constant presence. It is a stark reminder that life evolved to exist within the thin, protected cradle of our atmosphere. Fact 5. The volatile Sun. Fact 5 is the unpredictable nature of our own Sun. The Artemis II mission coincides with a period of high solar activity. Occasionally, the Sun releases sudden, massive bursts of plasma and energy called coronal mass ejections. If one of these silent solar storms sweeps across the spacecraft's trajectory, the crew could be exposed to acute, dangerous levels of radiation within a matter of hours. The Sun is not just a source of light. It is an active, volatile star. To mitigate this, weather satellites constantly monitor the Sun's surface. If an eruption is detected, the crew receives a quiet warning from Houston. They must then seek shelter inside the Orion capsule. They will construct a small, temporary safe haven by packing heavy stowage bags and materials around the central column of the ship. There, they will wait out the invisible storm, suspended in the quiet dark, while the solar wind washes harmlessly over their ship. Fact 6. The unraveling body. Fact 6 touches upon the physical degradation of the human body in space. Gravity is a constant companion on Earth, quietly signaling our bones and muscles to remain dense and strong. In the microgravity of space, this vital signal disappears. The body is highly efficient and adapts quickly to the weightless environment. Assuming that heavy bones are no longer needed, the body begins to reabsorb calcium. Muscle fibers, no longer working against gravity, begin to atrophy. Even on a relatively short 10-day mission, this physical unraveling begins immediately. The crew must carefully monitor their physical health, performing resistive exercises in the confined, floating cabin to mimic the pull of Earth. It is a slow, silent battle against their own physiology. The human form is perfectly tuned for the surface of a rocky planet, and in the deep void, it requires constant, deliberate effort to maintain its strength and structure. Fact 7. A loss of equilibrium. Fact 7 involves fluid shifts and the swelling of the body. On Earth, gravity constantly pulls the fluids in our bodies downward, and our cardiovascular system works hard to pump it back up. In space, without the downward pull, this liquid is free to redistribute. It naturally migrates upward into the chest and the head. This causes a persistent feeling of congestion, similar to a head cold, and a noticeable rounding of the face known as puffiness. This is a strange, subtle shift. The delicate pressure within the eyes can change, sometimes affecting an astronaut's vision. The brain also floats slightly differently within the skull, sometimes leading to motion sickness as the inner ear struggles to interpret the lack of gravity. The body is simply trying to find a new equilibrium in an environment where up and down have completely lost their meaning. It is a quiet, internal adaptation to the rules of a new world. Fact 8. The shadow of the moon. Fact 8 is the absolute silence of the lunar far side. As the Orion spacecraft swings around the back of the moon, a massive, 2,000-mile thick sphere of solid rock blocks all radio signals to Earth for approximately 45 minutes. Mission Control cannot hear the crew, and the crew cannot hear Mission Control. They are completely and utterly cut off from the rest of humanity. The telemetry screens in Houston will temporarily freeze in quiet anticipation. During this blackout, the 4 astronauts drift through the deep shadow of the moon entirely alone. It is a profound, uninterrupted quiet. They must trust that the automated systems and their trajectory calculations are correct. There is no one to ask for help, no voices from home to offer reassurance. They simply wait in the dark, watching the cratered grey surface pass below them, until the spacecraft emerges on the other side and the comforting static of a radio link returns. Fact 9. The kinetic return. Fact 9 concerns the immense speed of the journey home. Falling back toward Earth, the spacecraft gains tremendous momentum, pulled relentlessly by our planet's gravity. By the time the Orion capsule reaches the upper, tenuous edges of the atmosphere, it will be traveling at nearly 25,000 miles per hour. This is dozens of times the speed of sound. The transition from the frictionless vacuum of space to the thick blanket of air is abrupt and incredibly violent. The sheer speed creates an intense wall of compression ahead of the spacecraft. The air simply cannot move out of the way fast enough. The kinetic energy of their fall is rapidly converted into heat. For the astronauts inside, the quiet glide through space is replaced by the roar of the atmosphere tearing past the hull. They are essentially a falling meteorite, relying on precise angles to bleed off their speed without bouncing back into space or burning up entirely. Fact 10. The fires of re-entry. Fact 10 focuses on the extreme heat generated by this re-entry. As the capsule slams into the atmosphere, the compressed air creates a glowing, trailing wake of superheated plasma. Temperatures directly outside the window will rise to thousands of degrees, hotter than the surface of some stars. During the uncrewed Artemis I test, the heat shield experienced unexpected flaking and erosion under this immense stress, highlighting the razor-thin margins of survival. For Artemis II, engineers have carefully adjusted the re-entry path to reduce this stress. The heat shield is designed to slowly burn away, carrying the extreme temperatures back out into the wind through a process called ablation. Inside the cabin, the crew will watch the plasma dance outside their small windows, trusting their lives to a layer of specially engineered resin. It is a fiery, dramatic end to a quiet voyage, delivering them safely to the cool waters of the ocean. These 10 facts represent the physical realities of leaving our planet. They involve extreme energies, vast distances, and incredibly hostile environments. Yet, none of these things happen with malice. The vacuum of space does not feel anger. It is simply cold. The radiation is not cruel. It is just energetic. The engineers at NASA understand these profound risks. They manage them not with fear, but with careful calculations, quiet focus, and decades of gathered knowledge. As you lie awake tonight, consider the steady, methodical progress of the Artemis II mission. Think of the 4 humans drifting in the quiet dark, supported by the silent work of computers and the strength of a carbon fiber shell. Their journey reminds us of the delicate, precious nature of our homebrew world. Let the immense, quiet reality of their voyage soothe your mind. There is no horror in the stars tonight, only the gentle, persistent mechanics of our incredible universe. In the deep quiet of space, 2 small machines are making a very long journey. They are the Voyager probes. Launched in the late summer of 1977, they were designed to simply observe our local planets. Today, they have traveled further than any other human-made object. The concept of their journey is rooted in patience. Space is vast, and there is very little friction to slower moving objects. Once the rockets pushed them out of Earth's gravity, they simply coasted into the dark. They have been coasting in quiet isolation for nearly half a century. As of this year, 2026, Voyager 1 is roughly 16 billion miles from Earth. It is moving steadily through the constellation Ophiuchus. Later this year, it will cross a significant threshold. It will become the first human-made object to be 1 full light day away from us. A light day is an immense distance. It means that light, which travels at 186,000 miles per second, takes a full 24 hours to cross the space between the Earth and the probe. When Mission Control sends a command, they must wait an entire day for it to arrive. They must then wait another full day to hear a response. It is a slow, quiet conversation across the void. Voyager 2 is on a different path, traveling southward relative to the plane of our solar system. It is currently over 13 billion miles away, moving through the constellation Pavo. The Golden Record. Both probes carry a specific payload. Attached to the side of each spacecraft is a golden record. This phonograph record contains sounds and images selected to portray the diversity of life on Earth. It is a quiet greeting, a time capsule cast into the cosmic ocean. The records contain greetings in 55 languages, the sounds of wind and rain, and the songs of birds and whales. They are heavily shielded against the constant bombardment of cosmic dust. They are designed to last for 1 billion years in the unchanging vacuum of space. The Golden Record also carries specific images. It holds 115 analog photographs encoded into the grooves. There are diagrams of the solar system, pictures of human anatomy, and photographs of forests and oceans. It is a snapshot of our world in the 1970s. To play the record, a civilization would need to understand the instructions etched on its cover. These instructions are written in the universal language of mathematics and physics. They use the fundamental transition of a hydrogen atom from a basic unit of time and distance. This hydrogen diagram looks like two small circles connected by a line. It defines a specific frequency. Using this frequency, the instructions show how to construct an image from the audio signal. It is a logical puzzle, designed to be understood by any advanced intellect. The planetary encounters, the early years of the mission, were focused on the gas giants. Voyager 1 reached Jupiter in 1979. It sent back the first detailed images of the planet's swirling atmosphere and the Great Red Spot. It observed the volcanic activity on the Moon Io. Voyager 2 followed shortly after, using Jupiter's immense gravity to slingshot itself further outward. This technique, known as a gravity assist, allowed the probes to gain speed without using additional fuel. They borrowed a tiny fraction of the planet's orbital momentum. Next came Saturn. The probes navigated the complex system of ice and rock that makes up the planet's rings. They studied the thick, hazy atmosphere of the moon Titan. After Saturn, their paths diverged. Voyager 1's trajectory sent it upward, out of the orbital plane of the planets. Voyager 2 continued on to Uranus in 1986. It revealed a pale, featureless blue sphere rotating on its side. It discovered new moons and a faint system of dark rings. The probe then adjusted its course one final time, heading toward the furthest gas giant. In 1989, Voyager 2 arrived at Neptune. It found a dynamic, deep blue world with high-altitude clouds and incredibly fast winds. It observed the large moon Triton, noting geysers of nitrogen gas erupting from its freezing surface. This was the final planetary encounter. The interstellar mission. With their primary missions complete, both probes entered the interstellar mission phase. Their cameras were eventually turned off to conserve their fading electrical power. They no longer needed to look. Instead, they focused purely on feeling their environment. They use a variety of instruments to measure the magnetic fields, the sparse plasma, and the cosmic rays in their immediate vicinity. These instruments require very little power. They are powered by the slow decay of plutonium, their radioisotope thermoelectric generators. As the plutonium decays, the available electrical power drops slightly every year. Engineers on Earth carefully manage this dwindling supply. They turn off heaters and shut down redundant systems. They keep the probes functioning by maintaining only the most essential operations. In 2012, Voyager 1 crossed a boundary of the heliopause. This is the region where the solar wind, the stream of charged particles emitted by our Sun, is stopped by the interstellar medium. It marked the official exit from our solar bubble. Voyager 2 crossed this same boundary a few years later. Both probes are now fully immersed in interstellar space. They are surrounded by material expelled by ancient, dying stars millions of years ago. It is a completely different environment from the one where they were built. Engineering in the deep dark. The spacecraft itself is a marvel of resilience. The main antenna is a large, white dish measuring 12 feet across. This dish must be kept pointed precisely at Earth. If it drifts even a fraction of a degree, the communication link will be permanently broken. To maintain this precise alignment, the probes use small thrusters. These tiny engines fire in short, gentle bursts to correct the spacecraft's orientation. They use hydrazine gas as propellant. The computers calculate exactly when a small correction is needed to keep the antenna locked. Even the fuel lines for these tiny thrusters must be protected. If the lines freeze, the gas cannot flow. Heaters draw a tiny fraction of a watt to keep the temperature of the lines just warm enough. It is a delicate balance of thermal energy in an environment devoid of heat. The temperature outside the probes is incredibly cold, sitting just above absolute zero. Inside, small heaters keep the central computers warm enough to function. The computers themselves are ancient by modern standards, possessing less memory than a basic digital watch. Yet, these simple computers continue to execute their instructions flawlessly. They gather the data from the remaining sensors, package it into a faint radio signal, and broadcast it back toward the inner solar system. The signal is incredibly weak by the time it reaches Earth. The Deep Space Network. NASA uses the Deep Space Network to catch these faint whispers. Massive radio antennas in California, Spain, and Australia are pointed precisely at the coordinates of the distant probes. They listen carefully for the slow, steady transmission of binary data from the dark. This steady progress relies heavily on these ground stations. The massive satellite dishes on Earth must turn slowly to track the skies as the planet rotates. As one dish in Spain is site of a probe, another dish in California seamlessly picks up the faint signal The antennas must filter out the background noise of the entire galaxy, just to hear the weak transmission. It is like listening for a single whisper in the middle of a heavy rainstorm. The data transmitted back is very basic, describing plasma density and magnetic fields. Sometimes, the probes detect shockwaves originating from the Sun. Even past the heliopause, massive solar flares can ripple outward and compress the interstellar plasma. The Voyagers measure the passing of these waves. The changes are very slow, taking months to wash over the spacecraft. The sheer patience required to monitor this data is profound. A scientist might spend an entire career waiting for a probe to reach a certain boundary. The mission moves at a glacial pace, dictated by the vast scale of the outer solar system. There is no rush, only steady progress. The final silence. As the years pass, this signal will inevitably fade. The power will fail, and the radio transmitters will go dark. When that day comes, there will be no alarm. The screens in mission control will simply cease to update. The probes will transition from active machines to silent monuments. The silence will be the final stage of their existence. Without heat, the instruments will quickly drop to the temperature of deep space. The small amounts of fuel will freeze solid. The computers will stop processing data. The quiet will be absolute, yet their structural integrity will remain completely intact. The aluminum frames and the titanium fuel tanks will not rust or degrade. There is no oxygen to corrode them, and very little debris to strike them. They will remain exactly as they were built, frozen securely in time. Their physical journey will not end. They will continue to coast outward at thousands of miles per hour. They are moving so fast that they have permanently escaped the gravitational pull of the Sun. They will simply drift through the Milky Way galaxy for eons. In roughly 40,000 years, Voyager 1 will pass relatively close to a star in the constellation Camelopardalis. Around the same time, Voyager 2 will pass near a star called Ross 248. They will not stop or enter orbit. They will simply glide quietly past. Over billions of years, the probes will orbit the center of the Milky Way, just like the stars themselves. Long after the Earth has changed, and long after the Sun has expanded and faded, the Voyagers will still exist. They will be perfectly preserved by the cold vacuum of space. They represent the furthest physical reach of human curiosity. They are a testament to careful engineering and the steady application of physics. Their journey is a quiet, permanent mark on the universe. As you rest tonight, picture them moving silently through the deep dark. Sleep well.